Hello and welcome back to the Building HVAC Science Podcast. You may know by now it's our goal to create more knowledgeable HVAC and building performance pros so they can do better work and better understand each other and harmonize their efforts. Today's episode, I'll read you some quotes first. Most building failures aren't mysterious. They're just ignored fundamentals. Whoa. If you demand museum-level humidity, you're no longer building a house, you're building a museum. Moisture meters don't solve problems. They show you patterns. The thinking you employ solves problems. In this episode, Kaiser interviews Kohta Ueno, principal and co-owner of Building Science Corporation, for a wide-ranging discussion on building failures, moisture, HVAC, and the practical realities of diagnosing real-world problems. Kohta shares his unconventional path into building science from small remodeling jobs and a PBS NOVA episode to decades of forensic investigations alongside Joe Lstiburek, one of the field's most influential voices. The conversation quickly moves from origin stories into what really matters, how buildings fail, why those failures are often predictable, and how much cheaper it is to solve problems on paper than after construction. The major theme that comes up in this episode is moisture management, especially in high-performance and multifamily buildings. Kohta explains how seemingly small details like windowsill slope, back dams, airflow settings, and interior air seals routinely separate durable buildings from expensive failures. He also highlights a growing perfect storm in modern construction: oversized HVAC equipment, high ventilation rates, poor commissioning, and limited dehumidification, particularly in smaller units. Result is mold, humidity complaints, and systems that technically run but fail to control moisture. And I would add, fail to control comfort and fail to provide value. In this episode, Elk and Kohta close with a practical look at diagnostic tools and methods. Kohta emphasizes pattern recognition over single-point measurements, combining moisture meters, thermal imaging, pressure diagnostics, and blower-door testing to understand how air, heat, and moisture actually move through buildings. He encourages listeners to use freely available Building Science Corporation research and Joe Lstiburek's Building Science Insights as foundational resources, reminding the audience that most of the building failures are not mysterious, they're repeatable, understandable, and avoidable if the fundamentals are respected. And please take a look at the show notes. Tons of resources there. Okay, on to this episode where we hear from Kohta Ueno on mold, moisture, and missed details. Lessons from the building science trenches.
Hey everybody, welcome back to the Building HVAC Science Podcast. Kaiser here. Bill Spohn is not with us today. He's off doing something important, I'm quite certain. But we do have a very exciting guest with us. Mr. Kohta Ueno from Building Science Corporation is with us today, and he is going to talk about himself and a whole bunch of other stuff. So, Kohta, welcome to the show.
Great, Eric. Thanks for having me. This is fantastic to be on.
Yeah, I'm excited to get you on here. We've met a couple times in person, most recently down in Florida at the ASHRAE Buildings Conference. Was that Building 16, maybe?
Sounds about right.
Which is all about buildings. It happens like every 3 or 4 years, but it's the ASHRAE Buildings Conference. And this was my first time for that, and that was kind of exciting.
Yeah, it's a fantastic conference held every 3 years. A bunch of building nerds, both from the United States and Europe, both practitioners and academics all get together in sunny Florida in December to talk about all sorts of building enclosure or shell-related topics. And it's the wide range of things that are incredibly academic and geeky and have minimal application to the real world to people figuring out why condensation is happening all over their swimming pool.
Yeah, there was a lot of good info I took out of that class and the sessions that were in there in that whole event. So a lot of fun. But let's dig into you a little bit, learn a little bit about who Kohta is, and then we'll go into some other fun topics like Building Science Corporation and stuff like that. So why don't you tell us a little bit about yourself?
I'd have to probably preface that a little bit with Building Science Corporation, just so that people have the background story. So Building Science Corporation was founded by Joe Lstiburek back in the 1980s and 1990s, along with his wife, Betsy Pettit. Joe is pretty much the dean of North American building science, He was basically a fantastic person to have both as a boss and a mentor. He's done a heck of a lot to move the entire field of building science forward in this. So I am one of the current principals and owners of Building Science Corporation. Just to provide a bit of background on BSC, we pretty much made our bones back in the day with building forensic investigations, both the typical water leaks, mold, stuff is rotting, as well as the weird ones of, hey, we are getting dripping from the ceiling and it's on days that it's not raining. And we're the ones who are figuring out like, oh, it's an air leakage condensation problem that happens. And when the sun comes out, it melts all the frost and dumps down into your building, or completely bizarre ones like, oh yeah, the rain hits the brick on the outside, the sun comes out, blasts the moisture through the wall, and it condenses on your chilled water pipes in the ceiling. That building forensic detective work. Also, as a company, we basically took that expertise. We've worked with a bunch of new construction on the front end when the building is still on paper. It's always a lot cheaper to solve the problems when it's just lines on paper rather than it's up in the air. And basically looking at plans, figuring out this detail is going to be a problem. This is how we've seen it fail. Don't use this material, use that material. And on top of that, the company did a whole lot of research work in the past under the Department of Energy Building America program. That's some great fundamental work in the field of building science that was all done under of your tax dollars at work, government research that is now fully available to the public. Your question was about me in general. So my origin story is everybody gets into the field of building science some completely bass-ackwards way, and I'm included in that pile. So basically, I was done with undergrad. I was pretty burned out. I hung out my shingle as just a little small contractor doing messy little kitchen remodels and bathroom remodels for friends. Learned a heck of a lot, incredibly interesting, and I'm a terrible businessman, and I ended up living in my parents' basement. While I was living there, I saw an episode of NOVA on PBS, and Joe Lstiburek, my future boss, was one of the talking heads on that episode, explaining how he diagnosed the indoor air quality problems that were happening at the Massachusetts Registry of Motor Vehicles building. It was basically air leakage coming from outside into the return drop ceiling plenum, condensing on cool steel, causing delamination and the fireproofing getting into people's lungs and eyes. So my response was, oh, that sounds like a cool field. I like buildings and I'm an engineer. And it turned out that they were looking for an entry-level person right there and then. That was 1998. I've been with the company ever since, minus a few years off to get a master's degree with John Straub at the University of Waterloo in the field of building science. And I'm now currently one of the principals and co-owners of the firm.
That's a lot of information there. And I took some notes down from that we may dive a little bit deeper into. So 1998, we're talking 2026 right now. That's 28 years, if math serves me correctly in my head.
Yeah, that's about right.
That's quite a bit of time to be doing building science. So we're going to say you're probably pretty good at it at this point.
I managed to muddle through. There was always new problems to see, though.
And that's part of what I find so fascinating about the building science industry. And I came into it from the HVAC side, so I've got a little bit of a different take on a lot of things. But I find it very fascinating when I talk to people like you who have seen all these different things. And even in just our short conversation, like you've already brought out some really cool ideas in my head and thinking about, wow, there's another way to look at that, which I think is just absolutely fascinating. So the concept of finding issues before construction and finding issues on paper, I think is really a great one. Now, obviously, we've got a ton of buildings out here that we've got problems with and we have to go find this. But I'd like to dig into this solving problems ahead of time because, as you kind of alluded to there, it's always a lot cheaper to learn from somebody else's mistakes than have to repeat your own and learn from them, especially with buildings, because hopefully they're going to be around for a couple hundred years.
Absolutely. There's that famous line, always learn from others' mistakes. There's not enough time to make them all those mistakes yourself.
What does that process look like for you guys when you start looking at some of these things and trying to figure out what are these problems going to be or what could these problems be in a new building enclosure? And how does that relate to maybe some of the new materials that are coming out on the market today and how they behave? And maybe you have or haven't seen them perform before. Is the science still kind of the same behind a lot of things, or are there new products that are changing the way you do that?
Let's talk about the first piece of that, the process. So typically what I'm doing is an architect sends a reasonably complete set of plans. I go ahead, do a red line markup, say thumbs up, thumbs down on all these details, as well as what do you mean by this? And the drawings can vary all over the place. I've seen beautiful drawings where everything is detailed out. I've seen stuff where I'm wondering whether the architect has actually ever been on a job site and realizes that you don't use polyethylene to keep the rain out of your building in a roof deck, for instance. It varies all over the place. Then we typically have a call to Zoom meeting to go through all these markups. I explain why I'm making recommendations on various things. Like, this is a detail I've seen fail over and over, and here are my pictures of the failure. Let's not do that. And explaining the detail that I recommend to avoid those things. But getting back into your discussion on materials, I would say I'm a little bit on the front edge, a lot of materials. So people might say some things are new. For instance, continuous exterior rigid insulation. Some folks are just getting into it. We have research reports from our website going back to the early 1990s with all the pictures of this is how we've been doing it for a while. So it's not really that big of a jump for us. The new materials that probably are out there are the various vapor permeable self-adhered membranes on walls and roofs, the sheathing products that have a water control layer, air control layer, if we're allowed to say brand names, zip sheathing, and all of those other derivative or knockoff products that are out there. And all of them basically are very few of the new products that I'm seeing nowadays raise immediate alarm bells of, oh my gosh, this is the next EFIS failure, for instance. Just as background, for those who don't know their history, in the 1990s, they decided to take the product of EIFS, Exterior Insulation Finishing System, the synthetic stucco products, and move them from Europe to North America. And in that period, there were a massive number of failures. The epicenter of that was North Carolina. Basically, they went back to buildings that were a few years old, and the OSB sheathing was rotting. The fundamental reason is they used what's called a non-drained EIFS system, where once the water got past the surface, that visible stucco lamina, you were inside the vulnerable portions of the wall. Mold factory and rot factory was the result. My boss, Joe, made a bunch of money being an expert witness discussing why these systems are intrinsically flawed. That being said, everybody learned their lessons, and the majority of the EIFS systems nowadays are drained and very safe and very good. Like I said, a lot of these, quote, new products are not that new. For instance, zip sheathing, if this was the next EFIS, we would have seen it already. It's been on the market for a decade plus. Are there better products? Absolutely. But is it a disaster? Absolutely not.
Well, that's good to know. I see a lot of new houses going up with that. So I'm happy to hear that they might stick around for a while. Of course, there's a lot of details that go into that type of thing.
Oh, absolutely.
Let's transition a little bit into some of your field work, because you do a lot of field work now, investigating failures and things like that in the field. Are you seeing little details making a difference on things like, we'll say, zip system or something like that, like nail head sealing or seam sealing and things like that? Are you seeing any failures over even a shorter or longer period of time?
If you're talking about small details that cause failures as a big picture topic, the one thing that I want to hammer home that is valuable to probably your entire audience is window installation. So most of the manufacturers of both windows, water-resistive barriers, and other control layers, flashing tapes, make recommendations nowadays. You want to wrap the rough opening of your window with waterproofing. Just assume that your window will leak over time. You want to capture that water, keep it from hitting the vulnerable parts of your wall and draining out. We do this as a sill pan, basically your waterproofing wrap at the sill of the window that captures any of the water and drains it away. I've been at many investigations where we have either water problems or leaking windows where they did that wrap but they missed this really fundamental detail of you want to slope your windowsill or you want to put in a detail called a backdam, basically a raised piece of wood at the inboard side. The problem with just wrapping that window opening with waterproofing is that water hits that sill, 50-50, might go out and drain away, nobody sees stuff, or it might drain in, and your client is calling you back with a window leakage callback. That could all have been solved with just simply sloping the sill, putting in a back dam, and you would not be hiring an expensive consultant to come stare at your windows. It's just so basic and simple, and many of the failures I've seen just don't do it. Other components are you definitely want to drain that sill pan. I have a beautiful little video of, oh yeah, this window leaked. We pulled all the windows out, reflashed them, reinstalled the windows, and they leaked again, and that's why we're calling you. And basically, I slit the sill pan, the taped over bottom flange of the window. Yup, water came leaking out, which should have been draining out from day one. Instead, it dammed up and leaked inside. The last piece is the interior air seal on windows is super critical. This is not just an energy geek air leakage kind of thing. Basically, the interior air seal on the window, all four sides, typically low expansion foam, sealant and backer rod would be even better. That's critical to keep wind-driven rain out of that window to wall joint. You can think of the wind trying to force wind-blown rain through your wall, and if you have a good airtight joint on the inside of your window, that rain is just trying to blow into a closed bottle. It's just going to stop and not be able to drive that wind any further. Trying to keep wind-driven rain out without a good inboard seal, that's like trying to drag race with a tool chest chained to your dragster, frankly.
It's not going to work well.
It's not going to go well.
That's a great description. I love that. So somebody's going to do that on a drag strip now, I'm certain of. Try to drag strip with a toolbox attached to the back of a vehicle. That's some really poignant advice, I think, from the number of investigations. And you do quite a few investigations. How many do you think you're doing a year right now?
Probably at least once a month, twice a month, something in that range, and it varies all over the place. It varies from commercial, residential, all over the place. I've been doing a heck of a lot of investigations of recently built or renovated multifamily buildings with multifamily or hotel or similar with really bad humidity and mold problems. Sorry, bring this back to, I figure a lot of your audience is HVAC guys, and they might find this interesting. And some of them have to do with catastrophic air leaks. Basically, if it's hot and humid outside, you're letting air leak in the summer. Guess what? You've introduced more humidity inside. But a lot of that has to do with the mechanical systems as well. And it's become this perfect storm situation where equipment is oversized. The smallest we can get is 1.5 tons, and the loads on a north-facing multifamily unit with one wall, like 6,000 BTUs per hour at max load kind of thing. Modern high-efficiency equipment is worse at removing humidity than other legacy equipment. Modern codes are explicitly calling out for outside air ventilation, which means more outside air in summer, more humidity load, and as well as really poor installations. I've dealt with a bunch of them where they set 1.5 ton outdoor units and the indoor unit is set for 2 tons of airflow, getting like 500 plus CFM per ton. High airflow per ton means no dehumidification. Combine all of those things together and you have systems that are not dehumidifying at all, and we're loading up the building with moisture from outside.
That's a mess right there. And very common, it sounds like. I see it from a lot of my colleagues as well. And that becomes real ugly real fast. What do you think some potential solutions are that the industry could do to address that situation, given that we're seeing the number of problems with this?
Yeah, so specifically on that HVAC moisture side, I contributed to a fantastic Green Building Advisor article, 2-part series. We'll put that in the show notes. But one of the takeaways is there are fantastic HVAC techs out there. Great people like Brian Orr are trying to make the next generation of them. And unfortunately, the ones who are getting the contract to drop in boxes into a multifamily building are not the great HVAC techs, it seems, or they're not being paid enough to care, or they're not being trained well enough to do this. We can argue that more training, more standards, greater professional responsibility are going to be parts of the requirement. That's more than likely. Of course, that'll drive costs up. The more that the HVAC industry is competing with the same workforce that refuels nuclear reactors, the harder it is going to be to hire them.
Yeah, we need smart people to do a lot of different things. What about equipment? Do you think any changes to equipment or anything like that could be made? Would smaller equipment be appropriate? Smaller capacity equipment be more appropriate for this?
Yeah, absolutely. Smaller equipment sized for the loads that we're seeing in multifamily, high efficiency construction, maybe stuff that automatically adjusts to understand airflow. But there's going to be a lot of industry pushback, is what I understand historically. Like, for instance, I think Carrier or one of the majors put in an automatic fault detection system that would automatically pop up warnings saying, hey, we're detecting high static pressure and you should do something about it. And basically the installation community pushed back hard saying, we're getting this in every installation we're doing. Your system is wrong. It's like, no, it's actually alarming on the manufacturer's rated number. It's just everybody is putting in undersized ductwork.
And that's also another thing that you're spot on, I think, there. It happens a lot, unfortunately. And this stuff is, to me, it's like trying to drink a milkshake through a coffee stir.
Oh, absolutely. Yeah.
With undersized ductwork. And that becomes really, really difficult and takes a lot of work. And that fan just has to work that much harder to be able to move that air through there. Can it move it?
Oh, yeah.
Yeah.
Absolutely. Just as a for instance, in those cases where people set up the airflow for 2 tons when it should be 1.5 tons, I've literally gone in, changed the dip switches as a demonstration, and all of a sudden the airflow changes from freight train to silent. That's like, yeah, if you have the right amount of airflow going through, that works a lot better.
Yeah. So commissioning sounds like a big problem.
Absolutely. Yeah.
Some good commissioning, but that's interesting to me. Are you really seeing any innovative products out there that are solving that problem from an equipment sizing or a ventilation standpoint? Because I know you mentioned ventilation in there too. We're bringing in and trying to move quite a bit of ventilation air through a lot of these spaces, which of course brings in more humidity.
Yeah, a fantastic solution, if people can afford it, are those ventilating dehumidifiers like from Thermistor. Fantastic product. But if we're talking about 1,000 square foot multifamily units, the cost pressures on them are just insane. It's not going to be an answer. Unfortunately, there's not great answers that I've seen coming from the market so far. Smart people are probably thinking about this, but of course they're going to have to push it through marketing and sales and figure out, do we have a market for this? And what's our price point going to be so we can actually sell these things? And that's fundamentally going to be the hard problem. And whether or not the industry knows that this is a big enough problem that they should be doing something about it and pay for the premium equipment, I don't know.
Yeah. Maybe somebody listening to this will come up with some good ideas. Hopefully we've got some smart people listening here.
Yeah. Here's hoping for sure.
Here's hoping to that.
Yeah.
What other issues do you find and see in buildings that are pretty common that people should be looking for ahead of time, or even if they're walking in and finding problems?
A common problem, like if you want to give me something to chew on, like we're talking homeowner level or a builder level.
More builder level, HVAC contractor level. If they're walking into a building and say somebody's got high humidity and they're finding that in a house, or they're having a building failure issue, because we have a wide variety of listeners out here that we have everything from engineers to HVAC people to you name it, listen to this. So there's a big audience.
Just to kick out an example of a problem, if we're talking about a cold climate, Northeast, Midwest, seeing high humidity levels inside in the wintertime, that should be a red flag. And by high humidity, I'm talking 40%, 50% humidity in, say, Massachusetts, Maine, Minnesota. It's unlikely you're going to get there, but if that is the case, you should start to pay attention and start to worry. because the first tell you'll have in the winter, if your humidity is that high, is you'll probably see condensation on the glass on your windows. Those are probably the coldest surface in your house. On top of that, that's quite likely and quite possibly going on inside your walls. We've seen boatloads of cases of air leakage outward through your building shell. That moisture, the hot, humid air leaks outward, condenses on your cold sheathing, causes no end of problems in terms of rotting out your walls, rotting out your roofs. Basically, my boss, Joe, has said, humidifiers have caused more damage than bad architecture in terms of building durability and building disasters. I have a great set of pictures of a humidified building looking up inside the attic and seeing not just mold spotting, but full-on mushrooms that you could cut off and sell at the farmer's market growing out of the OSB.
That's impressive.
It was pretty terrifying.
Yeah, that's impressive and scary. I've never seen anything that bad, even in pictures.
Yeah. But takeaway is the drier you can keep yourself in the winter, the safer you are. I know this runs up against people who want comfort, people who complain about nosebleeds and dry sinuses. But if you can try to keep things 30%-ish in the coldest parts of winter, probably even drier if you're super cold like Maine or Minnesota, that's probably safer. If your client demands super high humidity, for instance, if they have specific health issues, or if they have an incredible art collection that they say, our art curator told us we cannot go below 50% relative humidity all winter long, and it has to be plus minus 2%. You are no longer building a house, you are building a museum, and you have to build your house accordingly based on those loads. Once again, to use an automotive analogy, you're talking about you need a F1 race car. You cannot drive a Hyundai with ball tires on this racetrack.
It's not going to end well.
Exactly.
And sometimes we do get those customers that have those high-end art pieces, high-end things like that we've got to think about that shell a little bit differently than a standard house. Probably one of the biggest complaints I heard in the HVAC field was people's flooring.
Oh, yeah.
That was probably one of the biggest challenges. I'm curious if you've seen in the retrofit world, if you've run across houses where they're doing a really good job, say, of retrofitting that shell on top of a house. And then even in the wintertime, we still get humidity driving up through like a concrete or a stone basement in an older house. How much of a problem do you run into with that?
So as background, BSC has done a whole lot of work on deep energy retrofits, basically trying to take an old 1950s, 1850s house and retrofit it on the outside typically to make it a better than code house. Like in a lot of these projects, we're talking about wrapping the house with a membrane, putting 4 inches of foam on the outside, upgrading to high-end double, triple glazed windows, super high R values throughout. In that process, you are definitely going to be improving the airtightness of your house, which is what you want. So it's definitely a possibility that a moisture load that was existing before, evaporation through a half-inch thick, terrible concrete slab in the basement, will go from a non-issue in a completely leaky sieve 1850s house to a potentially serious moisture load in a completely air-tightened house. So the takeaway is like retrofits are hard, especially on an existing building, which is pretty fundamentally what a retrofit is. So the takeaway is you do have to pay attention. If you have wet materials or other water problems, the answer is that has to be solved step 0 before you go start making your existing house into a near passive house level performance. So for instance, on that wet slab, jackhammering up the slab, building a new one, that's a fantastic solution. Taking your existing slab, covering it with a layer of epoxy vapor barrier paint, another solution. You have a rubble stone wall that leaks water throughout. Having some way of capturing that water, draining it to a French drain, covering it with a spray foam assembly, possible solution. Takeaway is new construction is so much easier in general than retrofits. Retrofits are hard. You have to think. Doing retrofits wrong can get you into trouble is absolutely true.
That's some good advice there. You really got to think through that whole process. And my experience has been water is one of the hardest things for us to visualize and really understand the flow and the transportation of it.
Getting back to what TrueTech does in terms of instruments, what you guys do is take the stuff that you cannot see or can only tangentially measure and make it quantifiable. So just as an example, moisture meters are stock and trade of what I use every day to look at these types of problems. My go-tos are Tramix, the little rubber pad meters, and Delmhorst wood moisture content meters. Great instruments. And what's often very useful is I'm looking at old buildings. I walk into an old masonry building, I see the entire wall of plaster bubbled and flaking off. And this building has been around since 1906. Take the moisture meter out, do some measurements, start to figure out, did this moisture damage, is this ongoing, or did this happen back in the Ford administration? I don't know unless I start measuring stuff.
That's a great transition there into, and this is a question I get asked a lot, what kind of instruments do I need to really go in and investigate these things? And moisture meters is something, we handle them. I know a little bit about them, but there's always knowledge out there that I can learn and anybody else can learn, I think. How many moisture meters do you carry? Do you find different types to be better for different surfaces?
Yeah, I only carry 2 of them with me. The Delmhorst, which is a pin-based wood moisture content meter, although you can also use it for gypsum board, for instance. But the one that comes out of my tool case all the time is a Tramix Moisture Encounter. It's a capacitance-based moisture meter. It has these 2 rubber pads. You set it down on a surface, and it measures basically the electric response of that substrate to the meter. And it can be used to measure wood, concrete, gypsum, plaster, basically a whole variety of materials. And typically what I'm doing on the masonry materials is a lot less about, oh, this number is safe, that number is not. It's way more about measuring patterns, where I'm basically walking around the building going dry, 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 wet. What's going on? And this wet is centered on this detail, a window, a pilaster, a corner, and then figuring out the why of that. Oh, there's a disconnected downspout on the outside of the building. We have ground contact and the water is wicking up from below. It's an outside corner. The corner of the building is cold, and therefore colder masonry ends up being wetter. There are all sorts of responses. So it's a lot less about the instrument itself. It's more about knowing the science of what's going on, what could be the mechanisms, and looking at patterns is how I have to put it. But back on the wood side, there are actually metrics. For instance, wood, if you're down anything below 15% moisture content for wood, you're basically safe. 20% moisture content, we're starting to get worried, although there's plenty of parts of buildings that go up to 20% and dry out just fine. 25, 30%, that's definitely the danger point. That's mold or structural decay levels of moisture.
Those are some good levels to run there. I like the pattern thought process to finding things, and that makes a lot of sense to me, and I think it probably would to other troubleshooters as well, is we're looking for that failure pattern, or we're looking for that location. And that's a pretty good methodology. I like that. What do you find when you're using that? Are you correlating anything with like thermal imaging or images to find that?
Yeah, so just an example of how this moisture meter can help me find things. I was in a basement in Holyoke, Massachusetts, and measuring moisture content on the walls and finding these little plumes of moisture below windows. I look closer, start scraping off the paint and realizing, oh yeah, there are small cracks in the concrete. They tried to repair it from the inside and painted over them, but that's exactly where the moisture is coming in. But getting back to your bigger picture point of what else am I correlating, thermal imaging is a tremendous tool that I think any building diagnostician should be using in general. My go-to is a FLIR, the C5, I think, the standalone camera, but the ones that plug into a phone, fantastic products. FLIR is just what I use, but there are plenty of great brands out there, and they can probably ask you for better advice on what the options are. And the thing to remember, though, is that All that an infrared camera tells you is surface temperature. People ask, that cold spot, does that mean air leakage? Does that mean thermal bridging? Does that mean water? Yeah, it could be any of these. You got to look and understand a little bit deeper to understand what's going on.
Yeah, thermal cameras have been unfortunately misrepresented by a lot of movies and TV shows.
Oh, yeah.
And I get this question a lot, like, can they see through walls? Well, I want to see what's behind that wall. You might want to go buy an X-ray machine because your thermal camera is probably not going to help with that.
Yeah, the most I've seen is where they have uninsulated radiator pipe inside the wall or the floor, and yep, you can pick those up if they're running, but that's about it.
Yeah, it has to be able to affect the surface of that wall that you can see.
Exactly.
And every time I see in the movies where they flip on the thermal camera and they all of a sudden see a person behind a full concrete wall, I cringe a little bit on the inside.
Oh, yeah, that's hilariously bad. Agreed.
That's a really great piece of information there, I think, to correlate those two. What do you find with regards to surface emissivity? Do you find yourself really resetting the surface emissivity on that camera very often, or do you pretty much leave it?
I'm typically leaving the emissivity setting at the default 0.9, but the takeaway is you should just be super aware of any shiny surface that you might be pointing your infrared camera at. Like there was one investigation where I was walking around the hallway, passing by the elevator, going like, holy cats, there's a massive thermal plume coming off the elevator door. It's super hot. And I start going around the corner and the thermal plume moves. Like, oh, it's a stainless steel door and that's my reflection. Duh. So the takeaway is if it's a shiny surface, go ahead and bob your head, move to the left, move to the right. If the thermal image changes, it's a reflection. You've just looked at an infrared mirror is how I put it.
That's a good one. Like I said, I get that question a lot of what should I do with this emissivity? And it's a challenging one. Have you taken any of the thermal imaging courses, like the different level courses, to learn how to use those cameras better? Do you think that's a good value add for people?
Yeah, I've not taken any of those courses, so unfortunately I can't really speak to that. But anything that provides useful, mostly I'm self-taught from figuring stuff out on investigations, but learning from others, anybody who can teach you those lessons and basically give you the guideposts to make that decision of, is this water? Is this thermal bridging? Is this air leakage? Anybody who can provide you more guidance on that front, also much the better, if you don't have that already in your back catalog of fundamentals.
Yeah, comes back to that. It's cheaper to learn from other people's lessons and mistakes.
Yeah, and one fantastic use of infrared cameras that I recommend highly is if folks are familiar with blower doors and air leakage testing, combining the two tools of a blower door test with infrared, basically depressurizing your building so outward air leakage comes in, doing that on a cold day or a hot day to find where the air leaks are. Fantastic tool as a quality control and understanding this is where the air leaks are at. On top of that, I thoroughly recommend, if you can afford it and sequence this, any new construction project, doing this type of a blower door infrared test before the interior finishes are on. Just trying to find where those air leaks are so when it's super easy to solve them and fix them, rather than, doing this test at the end of construction, finding, there's a giant air leak behind my fancy level 5 plaster finish. Guess we're going to live with that rather than ripping apart our plaster. Oh, well.
Yeah, definitely easy to find those problems early on in that new construction phase.
Absolutely.
What other tools are in your typical toolbox when you're going out and doing these investigations?
So I mentioned infrared camera, moisture meters of various kinds. I'm typically bringing along a couple of manometers, pressure meters, even if I'm not running an actual blower door test, figuring out is part of the problem the building is being super pressurized or depressurized, or pressure differences across various openings. That's another piece of things. Let's see what else is in my toolbox. Camera and a backup camera. A silly thing that I actually bring is a selfie stick so that I can, if I want to look at the conditions of a windowsill that's 10 stories up, I'm not trying to reach as far as I can out the window with my camera. I can actually get a picture of a parapet or other features like that. I know a drone would do an even better job, but this is what I can fit in my toolkit. Boroscope cameras, occasionally useful, but to me, if you can cut a hole, you'll probably learn a heck of a lot more. Occasionally, there are jobs where I am bringing along blower doors and duct blasters, but that's the rarity. Also, I do sometimes bring along temperature, humidity meters, especially if I'm doing HVAC work, basically measuring the temperature difference or the split across various units, as well as another fantastic tool I got from another of my mentors, Andy Ask, is an airflow meter. Basically, the same meter that you're using, you're doing a hot wire traverse of a duct. You can also use it to, when you're running a blower door test, to find, is this actually an air leak that I'm measuring over here? You just basically take your hot wire anemometer wand, put it in the suspected air leak, and it'll tell you whether or not airflow is going by there. Similarly, smoke pencils, Energy Conservatory sells a great little smoke dispenser.
That's a pretty good tool list there. I do want to go back to the manometers and say that I'm guessing that you're probably using what we would actually term as a micromanometer, something in that blower door range with the automatic zeroing and everything in it.
Yes.
Okay.
My go-to equipment is from Energy Conservatory. That's just who I grew up with.
Yeah, and that's fine. They make a great product out there. The micromanometers, especially in the HVAC realm, I find a lot of people asking, hey, can I take building measurements with the regular manometer that I'm making gas pressure measurements or even static pressure measurements and things like that? And there's a big difference between those two manometers. There's a cost difference, but there's a huge range difference. And the word that I'm looking for, accuracy is a little bit, but resolution is the biggest thing.
Absolutely.
They measure on a different scale. So I wanted to call that out, make sure that our listeners understood that.
Absolutely true. For instance, the type of pressures I'm measuring for buildings can be in the range of 3 to 5 pascals as a common type of metric. You can do that conversion to inches of water column, but the answer is it's super, super tiny. For those who don't have a mental image of a pascal, I believe the best explanation I've heard is it is the weight of a fly on the area of a penny.
That's pretty good. If memory serves me, an inch of water column is roughly 250-ish pascals.
Correct, 250.
So a lot of times where we're measuring in gas pressure, we're talking about 3.5 inches of water column is a normal gas pressure for like a gas furnace on natural gas. That's going to be a normal manifold pressure. So to convert those instruments into pascals, the numbers change a lot. So make sure, if you guys listening out there, you got to know what your tools can do. So we're running up towards the end of this here. I want to ask you for any final thoughts that you might have for our listeners out there, any final words of wisdom.
Just a final set of thoughts. I'm going to have to put a plug in for the research that my company did, Building Science Corporation. Website is buildingscience.com, and Joe Lstiburek, the founder, has put up all of his monthly ASHRAE journal columns on the website. So if you want a pretty fundamental and very entertaining education in the field of building science, go ahead to the website, go start looking at the building science insights. You can see everything from how Joe tells you how you want to build wine cellars, on why the space shuttle failed because of inward vapor drives, what stack effect is and how to control it, how to deal with it, HVAC in multifamily buildings. So many resources out there, and Joe is both an entertaining speaker and writer. And on top of those articles, Building Science was hired by the Department of Energy to do a bunch of research projects under the Building America program. We're no longer doing any of them, but this is literally decades of research work. All of them are posted completely for free on Building Science Corporation's website. Please make use of your tax dollars, download them, take a look, see these lessons that we geeked out on for everything from how to install continuous insulation on the outside of walls to can you dense pack cellulose a roof? No, you can, but you might have failures is the answer. A variety of topics along those lines.
A lot of good resources there. I've used a lot of them myself over the years and probably will use more of them in the future for different things. Kohta, I want to say thank you for coming on today. I know we didn't get to everything we wanted to talk about, and maybe we'll have to have you on again sometime and talk about some of the research you've done and some of your favorite ones. I'd really like to dig into that sometime.
Oh, sure. That would be fun, Eric.
Sounds good. Well, folks, thanks for listening. Kohta, thanks for joining us.
Thanks again. Take care.
Thanks again for listening to this episode of the Building HVAC Science Podcast. This podcast is a production of TrueTech Tools Limited. If you have any questions or want to suggest a topic, please reach out to us at marketing@truetechtools.com. That's TRUTECHTOOLS.com. And some topics we discuss require technical training, I would say like this episode, for proper interpretation or safe execution. So if you're a trained pro, you can proceed immediately. If you're not, please consult with a pro and hire one. And if you're a pro missing this kind of information, there are plenty of resources, many of those mentioned in this episode in the show notes, that you can latch onto and learn. I want to give a shout out to some other great trade-related resources and influencers, including HomeDiagnosis.tv, AC Service Tech, MeasureQuick, HVACX, HVACR School, HVAC Shop Talk, Stephen Reardon, HVAC Reefer Guy, Tool Pros, Service Business Mastery, Quality HVAC, HVAC Overtime, HVACR Videos, and the HVAC Grapevine. Thanks again for listening to this episode. We hope you're following us and subscribing so you can get these episodes fresh as they pop out of the Building HVAC Science oven. Hey, take care. Until next time.